Welcome back everybody for the second weeks of proceedings for this program. Today we will have 1 hour lecture, 1 hour plenary lecture on tropical variability by Professor Shang-Ping Shi. I hope I'm pronouncing your name in the right way. It's a pleasure to introduce Professor Shi. He's a professor at University of California at San Diego, at Scripps Institute of Oceanography. Professor Shi, thanks a lot for joining us and staying back a bit late. Over to you.
Okay, yeah, so thank you for the invitation. Today I'd like to talk a little bit about the modes of variability, both of monsoon, for monsoon, and also talk about the so-called coupled ocean atmosphere modes. And those modes gain persistence and coherent patterns from the coupled ocean atmosphere interactions. So some of those modes, you will see why the patterns are being determined by the coupling. Okay, so here I'm showing June, July, August summer rainfall distribution over Asia, Pacific, Indian Ocean, and then this is the red circled area is what we call a South Asian monsoon region, right? So with high precipitation on the west coast of India, Bay of Bengal, and the South China Sea. And there are other rainfall patterns we will touch upon maybe on the second slide. I guess the summer monsoon of South Asia facing the warm Indian Ocean, right? So the red contours indicate sea surface temperature at 28 degrees Celsius or above. And then the surface winds are indicated in arrows. So I clearly, as you know very well, the North Indian Ocean is characterized by prevailing southwesterly winds, right? All the way through South China Sea, and in August, September, the westerly winds even into far west and North Pacific. So these are the characteristics that you are probably familiar with. And then because the highest precipitation and strong diabatic heating in the deep convection over the general area of South and East Asia, the atmospheric dynamical response is characterized by a very large, right, transcontinental high pressure system at the upper level of the tropics. So this is what we call a South Asian high or Tibetan high. Basically, that this high pressure system displaces the westerly jet from winter position south of Tibet to summer position north of Tibetan Plateau. And then especially the westerly jet connects the Tibetan Plateau and Eastern China through Korea and Japan. Basically, this westerly jet anchors a rain band, as shown here, like slanted in the northeast direction. This is the summer rain band, very important for Eastern China, Korea, and Japan, and people call a Mayu rain band, right? So basically, this rain band is what we call East Asia monsoon. So East Asia monsoon is, in many ways, is distinct from South Asia monsoon, which you are familiar with, in that the Mayu rain band is fundamentally anchored by the westerly jet, for the reasons I don't have time to get into, but I just want to point out. the East Asian monsoon should be considered as actually tropical monsoon system, whereas India or South Asian monsoon should be considered to be tropical monsoon system. In a sense, the Mayhew Bayou rain band is going to subject to important jet dynamics. So this is just a very brief introduction, kind of orient ourselves both geographically and in terms of two major monsoon systems in summer. Okay, so importantly, both South Asian monsoon and East Asian monsoon exhibit a very pronounced interannual variability. And the interannual variability of the monsoon to some extent, and also it's going to be focus of my talk today, is the monsoon variability is closely related to the sea surface temperature variability in the Indo-Pacific Ocean. So if we do like a UF analysis of sea surface temperature anomaly, year-to-year anomalies, right, over the Indian Ocean domain, this is going to be the second UF explaining 12% of the total variance, which you are also probably familiar with, which features a cooling center off the coast, west coast of Indonesia, and a very broad warming over much of the rest of tropical Indian Ocean. So this is known to be as Indian Ocean dipole, right? So referring to the dipolar structure in the southeastern Indian Ocean and broad tropical Indian Ocean region. And then this so-called Indian Ocean dipole mode is known to develop in the summer of El Nino, right? So when El Nino, especially major El Nino events take place in the summer and fall, boreal fall, or in the Indian Ocean, you are likely to see this dipolar pattern. And then UF1 explaining 40% of interannual variance. It shows a pattern, kind of at least initially looks boring, right? So it basically is, the pattern is very flat. It's associated with the so-called basin-wide warming of the tropical Indian Ocean. Basin-wide, but not really uniform, at least in terms of amplitude, right? So enhanced loading in the South China Sea, and also enhanced loading in the southwestern Indian Ocean. I don't have time to get into details, but I guess in those regions of enhanced variability, actually there are interesting ocean dynamic variability involved, associated with upwelling in the marginal sea of South China Sea and in this open ocean, southwestern Indian Ocean. But it's sufficient to say, the SST variability is broken down into this so-called basin-wide mode and dipole mode. And then the dipole mode is associated with developing ENSO in the Pacific. And then this basin-wide UF1 is actually what is widely also known to be induced by El Nino seasonal oscillation. So El Nino itself peaks sometime in November, December, January, basically at the end of a calendar year. And then if you use November to January Nino 3.4 SST as the index, then you see the El Nino begins to develop in the summer, and then growing. This is a correlation, but in amplitude, it's going to grow and then decays rapidly in the following spring. And then by the next summer, the Nino 3.4 basically falls to insignificant values. But this UF1 is known to be highly correlated with Nino 3.4 index, but with the time delay. So in other words, the tropical mean sea surface temperature peaks about 2 to 3 months after the peak of El Nino. So this tropical delayed warming of the tropical Indian Ocean proves to be very important in generating and explaining Asian summer monsoon year-to-year variability in very important way. So this is just a quick introduction of the SST variability. So today the focus is going to be on this basin-wide UF1, right? So characterized by the basin averaged sea surface temperature anomalies. So here, previous slide shows you the auto-lagged correlation of Nino 3.4. So the correlation cannot tell you the magnitude of SST anomalies. But here is a raw SST anomalies for recent 4 major El Nino events, 1972, 82, 97, and 2015. So it's widely known El Nino is strongly phase-locked to the seasonal cycle. So in other words, I just said, it peaks in November, December, January of the calendar months. And then if you look at, the peak, this is a peak El Nino, right? So El Nino clearly has a signature, 6 months earlier in the Northern Hemisphere summer. There's robust warming already in June, July, August of the same calendar year as El Nino develops. But then for the decay year of El Nino, at least as far as June, July, August of the following years is concerned, the sea surface temperature anomalies all over the place, could be positive, could be negative, right? So basically, statistically, the correlation, the relationship in the decay summer of El Nino is not well defined. But there, as we will see in the next few slides, there are peculiar phenomena in the monsoon variability that there are very robust atmospheric anomalies in the post El Nino summer, right? So although post El Nino summer Nino 3.4 SST anomalies are not that robust, but for some reason, the Asia summer monsoon response shows a very robust response in the post El Nino summers. So that is the main focus, of my talk, namely, what causes this post El Nino anomalies in the Asian summer monsoon system. Okay, so to illustrate this, I will start from Indian rainfall, the rain gauge, the measurements, the rain gauge, the gauge measurements of rainfall in the network of Indian Meteorological Department. So there are hundreds of rain gauge stations over India, but I guess this is just to take the UF, the empirical orthogonal function analysis of Indian all the rain gauge stations, right? So the first mode explaining 20% of the year-to-year variance of the June, July, August, September mean rainfall. So the first mode is widely known, right? As can be represented by so-called all Indian rainfall index. So it's the average of all the meteorological stations in India, and then you can represent the time series of this UF1 pretty well. And it's also widely known this all Indian rainfall, summer rainfall index is highly correlated with Southern Oscillation Index, which is equivalent to a linear 3.4 SST index for the purpose of my talk. So anyway, so the first mode is just a uniform kind of a increase decrease of rainfall almost over the entire Indian subcontinent. And then the second mode, explaining only about 10% of the variance, is this mode is probably not as widely known as the UF1 because it cannot be captured by our Indian rainfall index because this mode has spatial pattern of dipolar structure. The northeastern India is in opposite phase with the southwest India rain gauges. So in other words, if you add all the station rainfall measurements together, it's going to amount, the sum is going to amount to nearly zero. So this mode is what actually, quite fascinating and puzzling at the same time. So this mode is correlated not with the concurrent El Niño. So it's not correlated with Southern Oscillation Index, nor linear 3.4 SST without, at the lag zero. But it's highly correlated with tropical Indian Ocean SST, especially North Indian Ocean SST, right? So recall the tropical Indian Ocean SST warms up at the time delay of 3 months following El Nino, right? So this will be the summer after El Nino, because that's when the tropical Indian Ocean tends to warm up. So this is one example of India, right? So not only Indian summer monsoon rainfall responds to the concurrent development of ENSO, but very kind of it's a little puzzling. It somehow remembers there was El Nino 6 months earlier because the tropical Indian Ocean is warm. So this is basically telling us, the post-ENSO effect on Indian rainfall is not direct, but rather through the tropical Indian Ocean warming, right? So this is important, kind of basically the conclusion, a general conclusion from my talk today. Okay, so this is all right. So I guess to the extent, the Indian summer rainfall relationship with ENSO has been studied extensively, as can be traced back to all the way to Walker's study 150 years ago. But I guess if you are a climate forecaster for East Asian countries like East China, Japan, Korea, this schematic diagram tells you nothing about ENSO influence on East Asia. Of course, nothing beyond. This plot, even in many other parts of the world, it notes nothing about the post El Nino, the ENSO influence beyond the spring when the ENSO events decay. So anyway, so I guess for climate forecast in East Asia, they like in India, the most important forecast is the rainy season rainfall, and this schematic definitely doesn't tell you anything about that. But I would, as it will become clear, there are robust recurrent patterns of rainfall variability in East Asia that can be robustly traced back to El Nino ENSO conditions 6 months ahead in boreal winter. We will kind of see that. Yeah, just to show you one example, right? So this is a box of rain gauge observations observed by China Meteorological Administration. So the leading mode for July is the midsummer months, right? So like for mid-July, for July rainfall variability, the leading UF explaining 21% of the variance shows somewhat a meridional dipolar pattern. So here the two rivers, the one to the south is the longest river of Asia, right? So this is the Yangtze River, and the one in the north to the north is the Yellow River. So clearly for this UF mode, for summer UF rainfall UF, the rainfall variability is almost kind of has largest loading along the Yangtze River basin, right? So you can imagine perhaps this mode is going to cause flooding when it's in positive phase of the Yangtze River. So this is a kind of the UF mode, right, with the high rainfall along the Yangtze River basin. And then the arrows indicate 850 hectopascal wind regression against this principal component UF1. So when Yangtze River is experiencing excessive rainfall, it tends to be associated with intensified southwesterly wind on the eastern part of China, causing kind of associated with the convergence of water vapor transport, right? And causing rainfall, increased rainfall along the Yangtze River basin. So this intensified southwesterly wind anomalies actually a part of a very large scale so-called anomalous anticyclonic circulation, right? So you can see this is a really very large kind of a, some people call this Western Pacific anticyclone, and in reality, this anticyclone is much beyond Northwestern Pacific, but extends into certainly it extends into Bay of Bengal and India, much of India, and maybe into Arabian Sea. So this AAC, anomalous anticyclonic circulation, you will probably see a few more times in my talk. And when it's in positive phase, in other words, if it's anticyclonic, that's when the Yangtze River is experiencing excessive rainfall. So this is a prominent mode of summer rainfall over East Asian region, and over this period, right? So this is like a 70-year period. This principal component is correlate with November, December, January Nino 3.4 index, 6 months ahead of the summer, right? So the correlation amounts to 0.3. So high, 0.3 for a 70-year record is a pretty significant, fairly significant. So there, in other words, this is a recurrent pattern because it's a UF leading mode, but it's also highly coherent and somehow co-vary with Anso cycle. So another thing to point out is it's correlated with winter El Nino 3.4 SST index, but not correlate with the concurrent Nino 3.4 index, summer Nino 3.4 index. In other words, somehow this anticyclonic circulation knows that there was El Nino in winter. So just to give you some examples, right? So this could be also called the post-Anso mode, right? So when you have a major El Nino happen in the winter, then in the summer following, you are likely to see excessive rainfall and this mode is going to be in positive phase. So, let's take a look. 1997 is a major El Nino, right? So the post El Nino summer is summer of 1998, and that's a year of major flooding along Yangtze River. And then 2015 is a major El Nino, and the post El Nino summer is 2016. In 2016, Wuhan is a city in the mid reach of Yangtze River. I've never been to Wuhan, but it's a city just by the Yangtze River. So for a short period, a week, right, in Wuhan, it received 560 millimeter rainfall, which is almost about 50% annual rainfall. And then you see the flooding on the streets. And then it's a big enough deal that Chinese Prime Minister came to inspect the damage, looking at the rising water level in the Yangtze River. So at least there are well-documented examples, major flooding events along the Yangtze River following in the summer, following El Nino in the winter. So another example is in 2016 post El Nino summer, right? So the first typhoon made a landfall in Taiwan on July 8th. So just give you a perspective for comparison, right? So a year earlier, in 2015, on July 9th, around the same time, the first typhoon made landfall in the following year, there were already 10 typhoons made landfall in Taiwan by this time. So in other words, in the post El Nino summer, there are very few typhoons in the Western Pacific, especially the typhoons making landfall near Taiwan. So very few typhoons following in the summer following El Nino. So these examples probably have convinced you there is indeed a post El Nino effect on rainfall and perhaps on typhoon in the Western Pacific. So just like we did with UF analysis of rainfall anomalies over India, and now we are going to do a much broader UF over much broader region of the Asia summer monsoon region, right? So just in this dashed red box. So the UF features the first UF explaining something like 30% of the variance. This is done over a period I forgot, 98 to maybe 2008 or 2018 or something like that. So it would be something like a 40-year period. So it's down on rainfall, summer rainfall, JJ rainfall. So the first UF features reduced rainfall over much of the Indian Ocean and maritime continent, and then there's increased rainfall. Oh wait, is that right? Yeah, this is the increased rainfall. Oh yeah. So this is the increased rainfall in the equatorial Western Pacific, but there's a decreased rainfall. It's a bit hard for you to see, but there's a decrease. Is this right? Oh yeah, this is correct. So the UF1, not surprisingly, is correlate with concurrent El Nino, right? So like Eastern Pacific warming, and then you have a westerly wind anomalies in the western half of the equatorial Pacific, and they have easterly wind anomalies over much of the equatorial Indian Ocean. And then if you look at carefully over India, right? So although the magnitude over the ocean is much larger in terms of rainfall anomalies, but over much of the India, rainfall is indeed decreased. It is indeed decreased, right? So this decreased rainfall is consistent with UF of rainfall over India. So the all Indian rainfall is this, and this mode is associated with the all Indian rainfall anomalies. So clearly this is a El Nino in development. So as indicated by the correlation between the principal component and the concurrent Nino 3.4 SST index. And then UF2 is fascinating. So explaining 15% of total variance. And it's clearly not associated with significant SST anomalies in the eastern equatorial Pacific Ocean. So in here, it's like blank, right? So no significant SST anomalies. But in terms of rainfall, you see it's associated with decreased rainfall from Philippines to the east, right? And then you see there's a large-scale anticyclonic circulation, right? So look at this, right? So this is familiar, as we have seen this anomalous anticyclonic circulation in association with July rainfall variability over eastern China. So this is clearly an anomalous anticyclonic circulation pattern. And this UF pattern is associated with a strong North Indian Ocean warming. So it's not correlated with concurrent Nino, but it's correlate strongly with concurrent North Indian Ocean sea surface temperature. So we can check the correlation with principal component, right? So it's highly correlated with concurrent summer North Indian Ocean SST, and it's somewhat less correlated, but still highly correlated with Nino 3.4 SST index 6 months earlier in winter. So this is what we call post-El Nino effect, right? So characterized by reduced rainfall over subtropical Western Pacific and anomalous anticyclonic circulation. So this is kind of reaffirming, not only over India and eastern China, but over much larger in the Western Pacific region, there is a post-El Nino mode, right? And I just want to briefly mention, if you look carefully over Indian subcontinent, you see there's dipolar rainfall anomalies, right? Between northeastern India and southwestern India. So they are in opposite phase. So that's exactly what we saw in the UF analysis over Indian subcontinent. So these examples, I think, leave a little doubt. There is not only concurrent El Nino effect on summer monsoon for Asia, but there's also a post-El Nino effect on the Asian monsoon, both over India and in China. So this is somewhat puzzling, right? Just given the seasons, the evolution of Nino 3.4, it peaks in December and then decays rapidly in the spring, and by summer the Nino 3.4 SSC index, this black solid curve already kind of diminished. It's almost zero, but there are significant rainfall anomalies and sea level pressure anomalies in the northwestern Pacific Ocean, all the way persisting through the northern hemisphere summer. So by this Nino 3.4 SST lag correlation alone, it might be puzzling. But by now, we kind of know perhaps the North Indian Ocean is the key intermediate between the winter El Nino and summer and anomalies of summer monsoon in China and India. So this is conceptually you can think El Nino also as a big battery, right? And the Indian Ocean as something like a capacitor. So when ENSO, of course, is kind of varies due to the couple ocean atmosphere dynamics of the tropical Pacific Ocean. And then it's going to charge the Indian Ocean capacitor. And then when the following summer comes, you even if you take away of the big battery of ENSO, the capacitor of the Indian Ocean would discharge and influence the Asia summer monsoon, at least through the summer following ENSO events. So that is kind of metaphor with the electric circuit, right? So Indian Ocean capacitor. So this is conceptually all right, but by what mechanisms, right? So how does this Indian Ocean capacitor discharge and influence Asia summer monsoon rainfall and circulation? So that I would briefly touch upon in the next few slides. So just kind of to let you know my plan. So I would like to leave the last 5 minutes also, for you to ask questions, or we can have some discussions, right? So maybe not long enough, but at least I would like to leave 5 minutes also. So if you have questions or things you would like to discuss in those 5 minutes, please raise your hand, and hopefully the host coordinator can see you in the classroom or in the chat box. Okay, so what happens is the following. So when Indian Ocean warms, it's going to kind of excite, we call the Gilles pattern, right? So it's going to, at the low level, you're going to see a low pressure Kelvin wave, and then there are two kind of Rossby gyres behind. So for the Kelvin wave, we are all familiar. Maybe we are mostly familiar with the Kelvin wave in the free troposphere, where the surface friction is not important. But in the planetary boundary layer, there's always a friction, even over the ocean. So the friction is going to drive the winds to gain a meridional component that is converging onto this low pressure on the equator, right? Along the equator in the Kelvin wave mode. And then this convergence is associated with off-equatorial divergence, right? On either side of the Kelvin wave wedge. And then this divergence, would induce a negative rainfall anomaly, and the negative rainfall anomaly is going to generate anticyclonic circulation in the lower atmosphere. So that is what the Gilles model, when we incorporate surface friction effect, might be telling us. So we will see next. So this is a kind of a schematic in a sense, right? But next, I'm going to show you the observed correlation maps. So this is the red contours are the free tropospheric temperature between 850 millibar and 250 millibar temperature anomalies, temperature anomaly correlation with linear 3.4 index in November, December, January, 6 months earlier, right? So this is basically saying, when you come to the summer, JJA, then the tropical Indian Ocean, especially North Indian Ocean, is going to warm up. And the Indian Ocean warming indeed excites this Gilles-like pattern, right? So the Kelvin wave propagating, the warm Kelvin wave propagating eastward, and there are some indication of off-equatorial Rossby gyre in the free tropospheric temperature anomalies. And now, as I argued earlier, right? So at the surface, you're going to experience the friction, and the friction is going to drive surface winds in the boundary layer. towards a low pressure on the equator. So then in our alpha equatorial region, you're going to see divergence, and divergence is going to reduce rainfall. So the gray shading with dashed white contours indicate negative correlation of local rainfall with NDJ Nino 3.4 index. So there's indeed a reduced rainfall in the alpha equatorial divergence. And then the reduced rainfall is going to reinforce this anomalous anticyclonic circulation. And this anomalous anticyclonic circulation is associated with intensified southwesterly wind over eastern China. And the rainfall correlation, for some reason, maybe this is a not earlier study, so it doesn't have a very long time record, at least for satellite observations. So the correlation is not super high, but it's marginally significant. But it's still kind of indicating there's increased rainfall in the Yangtze River basin. So this is reaffirming. It basically gives you a flavor of how the Indian Ocean capacitor will discharge and producing this anomalous anticyclonic circulation all the way through Bay of Bengal, India, and Arabian Sea. And then in the northwestern flank of this anticyclonic circulation causes rainfall to increase along the Yangtze River basin. Okay, so this is basically what I've showed you in terms of anomalous anticyclonic circulation, right? So now I have colored the arrows so that the red arrows indicate the anomalous winds are intensifying the background wind. So here the trade winds prevailing. So this is intensified trade wind. And then over the monsoon region, Arabian Sea, Bay of Bengal, and South China Sea, you see the arrows are blue. So the blue arrows indicate the anomalous winds are weakening the background wind, which is southwesterly, right? So in other words, when I said, in the summer following in post-El Nino summer, the North Indian Ocean is anomalously warm. And that anomalous warm condition, it acts like capacitor to generate or maintain this anticyclonic circulation. And this anticyclonic circulation is such that it's going to weaken the background wind in the North Indian Ocean, and reduce the background wind is going to reduce evaporative cooling, and therefore acting as anomalous warming on the North Indian Ocean SST anomalies, right? So here you probably already figured out there's positive feedback between the atmospheric anomalous anticyclonic circulation and the North Indian Ocean warming, right? So I guess if you were a meteorologist, you just say, anticyclonic circulation is there because the Indian Ocean is warm. Whereas if you were oceanographer, you will see the North Indian Ocean is warm. It's warm because the anticyclonic circulation, right? So you see a chicken egg argument that's usually indicating there's positive feedback. So the positive feedback between the ocean atmosphere is the reason why, in the post-El Nino summer, there are coherent ocean and atmosphere anomaly patterns in the broad region of Indo-Western Pacific Ocean, right? And as a result of this coherent atmospheric circulation pattern, you see the dipolar rainfall pattern over India, and you see increased rainfall along Yangtze River basin over eastern China. So this is the bottom is like the timeline. So ENSO peaks in December, and then preceded by Indian Ocean dipole, which we haven't talked about much. But then the Indian Ocean warming kind of follows the peak of El Nino and persists into next summer, partly because the Indian Ocean capacitor and Indian Ocean warming are mutually reinforcing each other, therefore allow long temporal persistence to on this kind of this atmospheric pattern and oceanic pattern to feedback positively onto each other. Okay, so maybe I'll skip this because this is a little complicated. So just to kind of because of the ocean atmosphere coupled positive feedback, that kind of gives us some hope. Maybe just statistically, if we know there is an answer event, right, in the body of winter, and all the statistical analysis I have presented indicated to us there may be some predictability in the summer for India and for East Asia rainfall anomalies, and in a couple, so that's statistical relationship. But these days you can have a global ocean atmosphere couple model, and if you provide the correct, accurate, appropriate initial conditions in the ocean, you should be able to predict the post-El Nino summer rainfall and circulation anomalies. And here I'm showing the ensemble multi-model ensemble forecast for three major El Nino events: 1980 post-El Nino summer, right? 1983 and 1992 and 1998. So in observations, you see a very robust anomalous anticyclonic circulation at the low level, and then that's clearly associated with Indian Ocean warming, right? And then in terms of rainfall, you see kind of a rainfall increase, the green increase the rainfall along Yangtze River Basin. And then over India, there's an indication of northeastern drying, and southwestern wetting. And then there's the tropospheric temperature shows like a characteristic wedge-like Kelvin wave signature. So that's the observation reinforcing what we have discussed. But then this is a multi-model forecast, right? Initialized, I believe, on May 1st of the year, right? So like maybe a 1 month lead. The lead is not super impressive, but still kind of the forecast, I think, is quite impressive. You see the anticyclonic circulation, Western Pacific, all the way through Bay of Bengal, India, and Arabian Sea. And then you see increased rainfall, and maybe excessively so, in the East Asia region. And then more importantly, this large-scale rainfall decrease that is associated with this low-level anticyclonic circulation. So all these patterns, major patterns, are well captured by the dynamical global couple ocean atmosphere model for these three summers. And this is work we done like more than 10 years ago. So we can now add more examples. But yeah, this is just to illustrate, at least for major El Nino events, there's a post El Nino effect that can be predicted at least 1 month in advance. Okay, so lastly, I just want to let you know that what I have talked about today, and more and plus more kind of a discussion on the Indian Ocean SST variability are presented, summarized in a chapter in chapter 11 of a textbook I published last year. So if you're interested, you could take a close look into this chapter. Most of what we talked about should be there. So thank you. And if you have questions, yeah, I'm very happy to answer or discuss.
Thank you, Professor Shi. There is plenty of time for questions. Yes.
Hello, is it audible?
Oh,
Good morning, Professor. This is Gokul from IITM Pune. So my question is about the recent summer monsoon. In August 2024, we saw a circulation pattern in the Indian Ocean that resembled a typical Gilles kind of circulation with twin Rossby waves and a Kelvin wave in the Indian Ocean and the maritime continent.
okay.
And that feature was around for a couple of weeks. And the Indian monsoon rainfall in that month was also below normal. And so my doubt is like whether the intra-seasonal time scale features like MJO in the equatorial Indian Ocean can it reinforce or trigger these kind of stationary patterns in the Asian monsoon domain?
Yeah, this is a very important point. I guess, a summer season, right? June, July, August, is only 90 days long. So if you have a major, people, what do people call the summer interseasonal oscillation or monsoon interseasonal oscillation, right? It could well screw up your seasonal mean anomalies. So in other words, here I focused on the year-to-year variability of the seasonal mean anomalies. But this is not to say the interseasonal anomalies are not important. And quite to the contrary, the interseasonal oscillations are very important, as far as a particular summer is concerned. And I guess that is why there's such a long history of intense kind of interest in monsoon interseasonal oscillation. I'm sure there will be more lectures and talks on this topic if they have not happened in this summer school.
Thank you.
Hey, Hi, Shang-Ping. This is Eric Maloney. How are you?
Oh, hi.
So have you looked at whether or not there might be any changes in these post-summer relationships in climate change, or maybe models, free running models can't get this relationship statistically? Have you looked at this at all?
Yeah, so I guess the record is of course people have talked about multi-decadal modulations, but that is hard to tell conclusively. But I guess in terms of CMIP model simulation of projections, there is some indication that those UF modes, right? The principal component, the temporal correlation with ANSO doesn't seem to change that much. But then, that's only the component that induced by the ANSO. But there's also those modes are also could vary due to internal dynamics. So the internal component of their variability does seem to intensify slightly in a warmer climate. So ANSO connection, not so much change, but internal component might become bigger. Yeah, in other words, maybe the predictability might decrease a little bit, I suspect. Yeah.
Yeah. Thank you. Are there any other students questions that students want to ask? Otherwise, I will ask one question of. Thanks a lot for a nice talk. I had a question about the capacitor effect that you mentioned. I was wondering, the Gilles model is a steady state kind of solutions, but in this problem, there's a bit of a lag between ENSO and the response. So I was just wondering, how is that lag effect incorporated in the interpretation. I understand also the Indian Ocean rate of cooling is reduced through the wind kind of response. But I was wondering, would the forcing really be will be steady, or something else might happen?
Yeah, so the atmosphere here, of course, we assume a quasi-equilibrium, a quasi-steady response to the atmospheric anomalies in quasi-steady state with evolving sea surface temperature conditions, right? So it's only the quasi-steady approximation or assumption applies only to the atmospheric variability. So that, of course, Madden-Julian oscillation is clearly not a great example for that quasi-steady assumption, right? But I guess hopefully for seasonal average anomalies, it's not too bad assumption. Yeah, of course, we have to take into consideration for intra-seasonal oscillations.
Any other questions? Yeah. Well, if not, please try out the book Professor Shi is mentioning, chapter number 11, and few other chapters. Yeah, let's thank Professor Shi again for this wonderful talk. Thank you, Professor Shi.
Thank you. Thank you.